Okay, let's talk about this. I wanted to do that because I kind of wanted to see again like how much of this is like immediately going in, or if it's just kind of I'll figure it out later type thing. Um, we have the area, right? We're trying to find the area in here. The best way to go about this, because this region is so weird, is to try and figure out if we can get a curve that encloses the area. Well, we're given the curve. I mean, we're given the parametric equation of the curve that draws out this epicycloid. So all we need to do is try and convert this over to a line integral. And we can use one of three formulas, right, from note 13.4.5. The one that I chose to go with was, I said, look, the area of a region D is the integral over the closed curve C of x dy. That's the one I chose. But you could have chosen negative y dx or that third one, but I won't mess with that. So I already know what x is, don't I? I already know what x is. It's given to me in the problem. X is 5 cosine t minus cosine 5t. And all I need now is dy, so I just take derivative of that y function. And I know my limits of integration are going to be from 0 to what? 2 pi. So this is going to become 0 to 2 pi. My x, which is 5 cosine t minus cosine 5t, that's x, times dy, the derivative of y is 5 cosine t minus, you have to be careful with chain rule here, 5 cosine 5t, and then dt. That's basically the setup of the integral. Then you have to multiply this all out. So let's just see what happens when we multiply this all out. What's 5 cosine t times 5 cosine t? 25 cosine squared t. Then you do 5 cosine t times negative 5, so that's negative 25. But then cosine t times cosine 5t. You can't put those together, right? That's just cosine t times cosine 5t. And then the inner ones, that's going to give us what? Negative 5. Isn't it again cosine t cosine 5t? And then the last ones here, negative negative is positive. 5, what? Cosine squared 5t. And then all of that dt sitting inside this integral 0 to 2 pi. These middle two are like terms, right? Those are the same. So that's negative 30 of those. And then 5 over here. Let me go ahead and power reduce that. Isn't that 1/2 plus 1/2 cosine what? 10t. I'll be able to integrate each of those. The first one I can do power reduce again over here, right? Does everyone understand the 10t on this? It's 2 times whatever was there. So if it was a 5t, if you power reduce, if it was a 5t, it becomes a 10t. And then that first one becomes, let's see, 25, again, 1/2 plus 1/2 cosine, this time what? 2t. The first two here, I'll write it out, 25 halves plus 25 halves cosine 2t. Let me pull those two from the back out front, plus 5 halves plus 5 halves cosine 10t. Can you integrate all those? You could put the 5 halves together with the 25 halves if you wanted to, but the antiderivative of a constant with respect to t is going to be just t with that constant, right? Antiderivative of this, you'll be able to find. Antiderivative of this. So the only real issue is that one in the middle. And how did you get that one? What's the formula you're using? Do they have a name for it? Does it name it on there? Let's see. Yeah. These are the multiple angle product to sum formulas for pre-cal. Product to sum formulas in pre-cal. Let me use it real quick. These are things that most people don't have memorized, but you should know they exist, especially when you're doing integrals. If you're doing integrals and you have a cosine times a cosine, and they don't have the same, what do you call that thing inside of it? Argument. They don't have the same argument, then you should be aware of this sort of formula. Whoa. Cosine u times cosine v equals, when I write it out, you might remember it. 1/2 cosine u minus v plus cosine u plus v. Thank you. And that's good that popped in your head, because that allows me to take that cosine t times cosine 5t and that negative 30 in front and turn it into negative 30 times what? 1/2. Then cosine of u minus v. So I'm going to go cosine of what? T minus 5t, which is negative 4t. And then the other one plus cosine of 6t. And now I have two terms, right? And I can just integrate those term by term. That's a great formula for breaking up products into sums, because it's easy to integrate a sum. It's harder to integrate a product. I'm not going to take it the rest of the way, but you could do each one of those now. You see how that works? All right. Oh, wow, we're almost out of time. Damn. See where we are here in the notes. Ooh, interesting. Were we almost there? We were almost there. Let me give you your homework, even though that last one we're not quite there on. The homework for this is page, crap, I don't know what page it is. I don't know, but it's 1 through 13 and then 17. 787? Thank you. 1 through 13, let's do odds. Now let me look back at this note, because I still have 3 or 4 minutes here. Y'all got that? Okay. Find this. What's different about this? What's that? It's a triangle, but something even before. It's a vector field, first of all, right? Look at the problems we've done before, right? Like this right here, we were trying to do this line integral, and it was something dx, something dy, right? So we haven't looked yet at how this is going to work. We'll save that for next class. Okay, I think it's too different right now for us to just look at. But I will say let's look at the triangle, right? I go from 0, 0 to 2, 6, 2, 6 down to 2, 0, back to 0, 0. So it's something like this. 0, 0 to 2, 6, back down to here, and then back over. So it looks like this. I go up, back down, like that, right? So we could find parametric. It looks like we could just do this traditional like we did before today, and we would just find the parametric equations for each of those line segments, right? And go about it. Or perhaps Green's theorem will allow us just to do a double integral over that triangle, which should be pretty easy because that's a type 1 region, double integral, right? Type 1 region. That's what we'll do next class. Okay? Isn't that better than having to do parametric equations for 3 different line segments? If we can just do a double integral over that region? Oh no, polar, yeah, polar's just been convenient. But we won't always stay in polar.